Hello everyone. So me and Virender are going to discuss a topic given to us by Arun sir. The topic is Takagi Sugeno fuzzy modeling for process control. The first part of the this topic will be taken over by Virender. So please continue.
Discuss topic of fuzzy modeling, and we will discuss the topic of the Saki Sugino fuzzy modeling. So let's start with the discussion. Let's first discuss about what is fuzzy model. Fuzzy model is a controller which uses fuzzy rules to define fuzzy controller. And fuzzy system use if then statement to involve fuzzy set, which involve fuzzy set, fuzzy logic, and fuzzy inference. Majorly, fuzzy role play a key important role in expert control knowledge, and it gives experience of linking the input variable of fuzzy controller to the output variable of the fuzzy controller. Normally, fuzzy rules are of two types: Madame fuzzy rules and Tasaki Sugino fuzzy rules. It is also known as TS fuzzy rules. Let's first familiarize with the Madame fuzzy rules. Madani fuzzy system. Let's take an example to understand the Madame fuzzy rule, which describing the movement of the car. If speed is high and acceleration is small, then the braking system is modest. In this equation, we have used speed, acceleration as the input variable, and braking is the output variable. Here, high, small, and modest is the fuzzy sets. And the term before then is known as input fuzzy set, and the term after then is known as output fuzzy sets. All variables here can be represented as a mathematical symbol. So normally Madame fuzzy system have three input and two output variables system. For example, if x1 is m1 and x2 is m2 and x3 is m3, then u1 is equal to m4 and u2 is equal to m5. The term before then is also known as rule antecedent, and term after then is also known as rule consequent. Here also x1, x2, x3 as input variable, u2, u1 are output variable, m1 to m5 are fuzzy sets. Now let's familiarize with the Saki Sugino fuzzy model. The Saki Sugino fuzzy model is nothing but a Madame fuzzy rules. But in output, we take the Saki Sugino use we use input variable as a function of output. Output is a function of input variable. Sorry. If x1 is m1 and x2 is m2, and then u1 is equal to f of x1, x2, x3, and u2 is equal to g of x1, x2, x3. Here, x1, x2, x3 are the input variable, and u is the output variable. So, output variable is a function of input variable, where f of x and g of x is a real function of time. Now, let's familiarize with fuzzy inference system, which is also known as fuzzy rule based system. This here is a block diagram given which describe the fuzzy inference system. Here, the first is there are five conventional blocks used in this fuzzy inference system. First is rule base. Rule base it contains the number of fuzzy if then rules. And data next is database. It defines the membership function of fuzzy set and which are used in fuzzy rules. It have a decision making unit which perform inference operation between the rule based data set, and we have input which are given to fuzzification which perform the transformation of Chris input into the degree of match with the linguistic values, and the defuzzification interface block, which transform the fuzzy result of the interface into the crisp output. Now we will discuss how the construction of fuzzy model is done. The fuzzy model design approach, we need the Saki-Sugeno fuzzy model as a nonlinear mode system. There are two approaches for construction of the fuzzy models: identification using input-output data and derivation of the Saki-Sugeno fuzzy models from the nonlinear system equation. This is the block diagram how we can construct the fuzzy models. First, we have a nonlinear system. We have to identify the system parameter using input output data, and then it is given to the TS fuzzy models and the fuzzy, and after then fuzzy controller, then the fuzzy controller gave us the out. The two main part which we have to calculate here is structure identification and parameter identification. Here, identification approach to fuzzy model is suitable for plant which are unable or too difficult to be represented using physical model. To handle nonlinear dynamic model, we have a second approach which derives fuzzy model from the nonlinear dynamic model. This approach uses the idea of sector nonlinearity and local approximation or combination of both to construct the fuzzy models. Let us discuss about sector nonlinearity. Sector nonlinearity, we have considered a simple example of nonlinear system where x dot is a function of xt, where f of 0 is equal to 0. Here our aim is to find the global sector such that x dot will become the function of x only, where this nonlinearity is belong between a1, a2, xt. Here, as we see from the graph, the nonlinearity lies between the a1xt and a2xt only. So this exactly defines the fuzzy model, and this sector nonlinearity guarantees that the exact fuzzy model is being constructed. We sometimes we have find difficulty to find the global sector for general nonlinear system. So then we have considered the local sector nonlinearity. In local sector nonlinearity, we have considered two line which became the local sector under minus d to plus d, where xt belongs minus is lie under minus d and plus d, and from minus d to d, this nonlinearity exactly defines the fuzzy model construction. Now, after this, we have mathematical model of fuzzy controller. So let us take a non-linear system. X dot is equal to x2 and xt is x1 square plus x2 square plus u. Our aim here is to derive the Tasaki-Sugeno fuzzy model from above non-linear equation using the sector non-linearity approach. We have assumed here x, which is a fuzzy variable, which is 0.5 and 3.5, and x2 belongs to minus 1 to 4. X1, x2 are non-linear here. Let's x1, x2 we can denote it as z1, z2, which is also known as premise variable. They may be a function of state variable, input variable, or external disturbance or time. When z1 is equal to x1 and z2 is equal to x2, we can write the x dot of x of t is equal to 0, 1, x1, x2 into xt. This is the nonlinear model. We linearize it and put it in x of t, x dot of t. Now we have here to assume that the permissible variable are just the function of state variable. For just for simplicity we have taken it, because if we not take this, our defuzzification will become very complicated. So to avoid this, we have to take permiss variable as a state variable. To achieve membership function, we have to calculate the z1t and z2t. Z1t is the maximum value, we have to consider z1t maximum value and z1t minimum value. Similarly for z2 permissible variable, here x1 x2 represent the membership function m1 m2 n1 n2. We can write z1t is equal to xt in a linearized form, where which is equal to m1 into permissible variable into the weighted average. And according to this we, and we similarly we can write x2 equation and z2t equation, considering n1 z2t and n2 z2t. Now according to the fuzzy mathematics, m1 m2 and n1 n2 are actually fuzzy sets, which can describe as m1 zt plus m2 z1 of t is equal to 1. Similarly, n1 z2t plus n2 z2t is equal to 1. Now we have assigned the name to the membership function, like m1 we call as positive, m2 we call as negative, n1 big and n2 is small. Like this we assign a name to a membership function. Now we have considered the for now we have to consider the permiss variable z1t. We have here the minimum value and the maximum value. For minimum value we have considered negative, so it is negative m2 z1 of t and m1 z of t for the maximum positive. Here similarly for x2 permiss variable -1 and 4 we have given before. For -1 which is a small value and 2 z22, and for big value and 1 z2t. Model rule ith, from model rule ith, if z1 of t is equal to m1 of I, and similarly we, zp of t is equal to mip, then x dot of t is equal to a1 xt plus b1 u2, which is a subsystem of this nonlinear system. Y is equal to c1 xt, where I is equal to number of fuzzy models. I belongs to number of fuzzy model suits up to R. Mij is a fuzzy set where xt in this equation is a state vector, ut input vector, and zut is permissible variable. Here we have to define the rule. So model rule 1 says that if z1t is positive and z2t is big, means z12 is positive and z2t is big, then we have 3.5 and 4. So we can write x, then x dot of t can be write as a1 of xt, which is a subsystem. Similarly, if z1t positive and z2t is small, z1t is positive and z2t is small, then we have another system subsystem which is a2xt. Similarly, we can write mode rule number 3 and rule number 4. These subsystem can be written as in the matrix form, where a1 is equal to 0 1, here maximum value of z1, here maximum value of z2, here max for a2 variable, here 0 1 maximum and small, here for a2 small and big, negative, negative and big, and negative and small. So now x dot we have, now we can derive x dot out of defuzzification process. So x dot will become h1 zt a1 xt, and similarly the function, we have different subsystem. According to that we will assign weight to them. H1 of h1 h2 h3 h4 are the weighted function. Here h1 z of t is m1 z1t into n1 z of t. Similarly, we can assign weight to all h1 h2. The Saki-Sugino fuzzy model exactly represents a nonlinear system in the region x1 belongs to x2 into x, and these x1 x2 is a space. To clearly understood, we have to calculate the output of x dot for specify value of x1 x2. for this we have to write this rule again. For this z1 t is positive, z2 t is big. For x1 is equal to x2 and x2 become 2, positive is big, so 3.5 and 4 we have taken the value from this model. And similarly we have to write z1 of t positive. We have write 4 subsystem here using this table. In this matrix we have 4 subsystem. Now we have assumed that z1 of x1 is equal to 2.75 and z2 is equal to 0.25. Now we can draw this diagram again, and we have to select the premise variable and consequences of this and the truth table for this. So for m1 z1 at 2.75 we have value 7.718, and for m2 well we have 0.218. Here for at z1 n1 z2 value is 0.25 and n2 z1 value is zero point 0.5 and n2 z2 value is 0.75. We have assigned this as based on the rules. So now we have a consequence which we write this subsystem. We can write this subsystem as this and putting the value of x1 x2, which is 2.75 and 0.25 we have considered before. After solving this we can find the truth table of permissible variable. We have find truth table using AND gate, which we have this permissible variable into x1 dot, and then the result of this we will get that the minimum function, because we use AND function here. The result is that we we get the minimum function out of these. The final value of x1 x2 x1 dot and x2 dot is a fuzzy defuzzification process. X1 dot can be written as the point 2 x1.
Hello everyone. So I am going to discuss the following example which is given here. So there are two things given here, x1 and x2. The state space is given as x1 dot is equal to x1 t plus x1 into x1 into x2 cube. So for simplicity, it's assumed here that the range for x1 and x2 are -1 to 1. So like just Virender told in the previous example, we have to take it as x dot is equal to some function a into x. So that the function will be here as such -1 x1 x2 whole square, and below it will be 3 plus x whole multiplied by x1 square and -1. This is the equation we got from 2.10. And uh, let's as Virender already discussed, we will assume those nonlinear terms as z1 and z2. So here x1 uh, multiplied by x2 whole square is being assumed as z1, and z2 will be x1 square multiplied by 3 plus x2. So this is the equation which we get. So now we will calculate the maximum and minimum values of Z1. So maximum values of Z1 will be 1 because x1 and x2 whole square. So x2 will be 1 and x1. So it will be 1, and minimum of Z1 will be -1, as in put the value of x2 whatever and x1 is 1. But the maximum value of Z2 is 4 and minimum value of Z2 is 0. The minimum value of Z2 is 0 because uh, like even if we put x2 is equal to -1, we will get the positive output because x1 whole square is positive. So we put x1 is equal to 0 such that we get the minimum value of z2 is 0. So next, see, and now we got these four values, and like we will discuss now z1 z2 in terms of m1 and n2. So the z1 can be written as m1 into 1, that 1 is the maximum of Z1, and M2 into minus 1, like minimum of 1. That is Z1 is a linear combination of like the maximum and minimum values of Z1. Similarly, Z2 is a linear combination of uh, Z2. Z2 is a linear combination of maximum value of Z2 and minimum value of Z2. So the equation is written as N1 into 4 and N2 into 0. So as Virender discussed earlier, like M1 plus M2 is equal to 1. Similarly, N1 plus N2 is equal to 1. So like we get two equation in terms of N1 and N2 and M1 and N2. So like solving these two equations, like we can get the value of M and N in terms of Z1 and Z2. So like just for simplicity, we name the membership functions as positive, negative, big and small. Like Z1 has positive and negative, and Z2 is big or small. So let's say rule one. Rule one, like it has four, so two to each. So there can be four combinations. Each model rule represents one combination. So let's say Z1 is positive and Z2 is big. So like it will be x dot is equal to ax1. So similarly other four combinations will be the same. So let's like going to model one, the a1 will be -1, 4 and -1. So we get this by using this equation, x dot is equal to -1 z1 z2 -1 xt. So here both Z1 and Z2 are in their like positive and big values. So we will use maximum of both of them. So maximum of both of them there are 1 and 4. Similarly, let's say for model rule 4, so Z1 is negative and Z2 is small. So like the Z1 will be the minimum value of Z1 and Z2 will be the minimum value of Z2. So here by this way we define four model rules and accordingly four subsystems. So here are the membership functions and like M1, N2 and N1, N2. So like we did in last question, like we can get the x dot t as in like the weight function multiplied by a subsystem into x. So the weight function will be we will get by like there are four model rules and each model rule represents a single weight function, as in like h1 represents m1 into n1. Like model for model 1 it will be m1 for positive and n1 for big. Similarly for this 4. So like this fuzzy model rule, like x dot this rule, this represents the exact system in the nonlinear region of the in the range -1 and 1. So like Arun sir shared a YouTube video, like the simulation part of any fuzzy model. So this is the fuzzy model which we are given, and its simulation is given here. This is the simulation part. This is the simulation part of the example just now I discussed, like this one. This equation has get this simulation, and accordingly we will get the time response of the fuzzy model. This will be the time response, and this is the like function surface. Like this is the same what Arun sir shared in the video. So now my next topic will be local approximation in fuzzy partition spaces. So like in TS fuzzy model, it is also a way to solve equations, but the like advantage of here is key, we can reduce the system in a like and to make it very easy. For example, here let's say inverted pendulum question. So in inverted pendulum, we take around 16 fuzzy rules to describe the system or to model the system. But if we use local approximation in fuzzy partition spaces, by this we can like describe the system even in 2 or 4 rules. So like this way it helps us to reduce like lengthy models. Now I am going to discuss a like example on inverted pendulum, which I just gave. Like so, the state space is given by x1 dot is equal to x2 and x2 dot is equal to gx1 am. Like this is the state space where x1 denotes the angle in radian and x2 is x1 dot. So it is the angular velocity, and g is the gravitational constant. F given the mass, and capital M is the mass of the cart on which the pendulum is balanced, and 2L is the length of the pendulum, and U is the force applied. So as we can clearly see, the state space is a nonlinear system. So like uh, when x1 is around 0, like the angle is 0, the nonlinear equations can be simplified by x1 dot is equal to x2, and x2 dot is equal to gx1 minus au by 4 L by 3 by am. Like we can see that these both are both after that approximation, when x is near to 0, the system becomes linear. Similarly, when x is near pi by plus minus pi by 2, then we again like substitute the pi by 2 here, and see that here also both the systems are linear. Okay, so we can say that, like, using local approximation, we can assume a nonlinear system using fuzzy rules to become a linear system. So um, see, there are two models. One is for x is equal to 0, one is for x is equal to plus minus pi by 2. So for both of them, uh, like there we declare two subsystems. First one will a1 into b1 a1x in plus b1u, and for model 2 a2x plus b2u. So like it is to be mentioned that here, like when x is about plus minus pi by 2, the modulus of x will be less than pi by 2. Like it will be less than pi by 2. So like here we can see that the subsystem will be x1 dot is equal to x2, like 0 and 1, and this one will be g by 4L by 3 minus AML. So and there is the x2 dot is not depending on any x2, so the x2 part will be 0. Similarly, from this equation, we arrive at the subsystem A2. And now, like here we can see there is another variable which is taken. It is beta. The beta is a constant which is cos 88 degree, which we got using the approximation near these values. So we can see that because there are two rules, the membership functions can be defined here, like minus 90 and plus 90. When it is minus 90, 0 to minus 90, and minus 90 to 0. In both cases, rule 2 will be applicable, like it will be little less than this one, like pi by 2. And when it is around 0, like 1 around 0, so we will use model rule 1, and in between them we can use fuzzy rules. So uh, suppose like if the non a pendulum is given in such a way that the pendulum revolves in a whole circle, that is, the limit is from minus pi to plus pi. Okay, so in this subsystem we have to include those pi parts as well, because the, like, rather than getting into half circle, it will uh, revolve in a full circle, that inverted pendulum. So in even in this case, the first two will be same, as in x1 when x1 is about 0, then a1 into b1 a1, and x, like a2 and b2 when x is around pi by 2. And see, the both of their rules are, for one case x will be, the mod of x will be less than pi by 2, and the mod of x will be greater than pi by 2. Here is the difference between, like, mod rule 2 and 3, and for model rule 4, it's around when the x is around pi. So we see that when we assume all these things, we get the state space as linear state space. So similarly, we assumed earlier, we get the same values of a2 and a3 uh, because the approximation is nearly same. So all the systems are linear. So from here, after simulation, the time responses of the inverted pendulum after giving fuzzy approximations, we have got like this. And like for if the pendulum revolves a whole, so it will be around, like, for positive it will go to 0 to 180, and negative it will go to minus 180. So here we describe four rules, like when it is around 0, so rule 1, around plus 90 to minus 90, it will go through the rule 2, and after those around 180 plus minus 180, it will go by rule 4, and rest is like rest can be considered in rule 3. So like we did in previous example, this sort of inverted pendulum can also be solved using Simulink implementation. So here is a Simulink circuit given here. So this is the whole thing which is described, and so our presentation is completed. So I have completed my part.
I also completed my part. Now, in last, we say thank you.
Thank you, sir, for giving us this assignment.